Thank you for joining us for another MOLYKOTE webinar. This will be reviewing the L.E.T.S acronym. We have Cassia Hegel with the DuPont team application specialist. She will be walking through this presentation. Thanks, Cassia.
So for today's presentation, we'll be reviewing L.E.T.S, the MOLYKOTE acronym that we use for lubricant selection. So to begin, we'll begin with an overall review of MOLYKOTE, starting with the product range, specific MOLYKOTE solutions, Tribology 101, and then the lubricant selection process as a whole. So to begin, MOLYKOTE has a pretty comprehensive product range, which encompasses multiple product chemistries, which can be selected for specific application requirements with specific performance parameters in mind. Oftentimes, we'll select products based on compatibility between an application in a specific chemistry set. For example, a commodity non-synthetic base oil like mineral oil would likely not match a high-performance requirement or capabilities that a synthetic base oil such as PAG, which is a polyalkyl glycol, or a diester would be able to provide, especially in regards to performance requirements like oil bleed, wide temperature, and load carrying capabilities. So the MOLYKOTE portfolio encompasses a number of product families, including greases, pastes, oils, compounds, dispersions, and anti-friction coatings. And when identifying a particular lubricant for a specific application, we use the acronym L.E.T.S, which stands for load, environment, temperature, and speed. Depending on specific application parameters, the overall function of the lubricant itself will vary. The lubricant may function to either separate surfaces, reduce wear and friction, manage contamination, protect against corrosion, or provide electrical and thermal management or transmit power. Additionally, when we consider lubricant selection, it's also important to consider the friction dynamics in a tribological setting. To understand friction dynamics, we study tribology. And tribology is the study of friction and wear between moving interfaces. And the concept of tribology can be broken down into three separate friction regimes, including boundary friction, mixed friction, and hydrodynamic friction. So boundary friction would involve slow-moving, high-load applications. An example of an application involving boundary friction is press fitting. For applications involving boundary friction, we often lean towards the selection of pastes and anti-friction coatings, which are lubricants in which the solid lubricant itself is acting as the primary lubricating agent. In those cases, it's important to consider the capabilities of the solid lubricant in the formulation when selecting a chemistry set for the specific application. In contrast, a hydrodynamic friction regime would encompass fast-moving, low-load applications. For applications involving hydrodynamic friction, we would typically select a grease or a fluid. In those product families, it's the base oil itself that's acting as the primary lubricating agent, not the solid lubricants. Mixed friction regimes would include a mix of both. Both friction regimes, it's a mix of boundary friction and hydrodynamic friction. And in those such applications, we tend to select either a grease or a grease with a solid, like one of the grease pastes within our portfolio, or a dispersion, which are usually solid polymeric additives suspended in almost like a high purity solvent in order to form a semi-dry film. Also within the portfolio, a lubricant can be selected for enhanced functions as well, beyond just friction and wear, and that's what we call MOLYKOTE Plus X. And depending on the application needs, a lubricant can be selected either for electrical or thermal management, corrosion mitigation, oxidative stability, dampening / noise, vibration, and harshness control, or for green labeling. So it's important to understand some of the basic concepts in tribology when considering lubricant selection. One of the primary functions of a lubricant is to separate two interfaces in order to reduce friction and thereby reduce heat. By reducing the friction between two interfaces, you can reduce wear on parts and therefore extend asset life. We consider all interactions between the mating surfaces, which is why we often use the L.E.T.S acronym during lubricant selection. the load being applied to two moving surfaces as well as the speed at which the two interfaces are moving, if at all moving, is important to consider. A high load at a slow speed may warrant the use of a paste, whereas a low load at a high speed may warrant the use of a grease in contrast. Additionally, some applications at more extreme conditions would also require additional, more specialized additives. For example, the lubrication of a metal flange pipe may require grease with corrosion mitigation additives in order to prevent crevice corrosion in chemical processing or in applications involving upstream oil and gas markets. Additionally, temperature is important to consider as well, because applications requiring a wide temperature range would require the selection of a more premium, high performance enhancing base oil or additional additives as well. So overall, we can summarize the lubricant selection process in 6 steps. So the first step of selecting a lubricant would be to define the application in tribological terms by determining the friction dynamics of a given application. Doing so would give insight into which product family to first select. Next, you can define the application using L.E.T.S. By defining load, environment, temperature, and speed, you can determine the correct chemistry that's needed within the lubricant. Sometimes more specialized applications may require more specific additives for targeted performance, like we had gone over previously. For example, power control modules have aluminum and plastic clamshells, and the lubrication of elastomeric seals may require grease with corrosion mitigating additives. Additionally, you may want to consider long-term reliability and fail operational needs. And as you consider current and future design needs, you could also engage MOLYKOTE SMEs in order to determine the appropriate solutions. So next we'll go over a couple of case studies in order to apply L.E.T.S in an actual application setting. So the first application we'll go over is an inverter operation for battery life. So the challenge in this specific application is elastomer compatibility. So we need to select a lubricant that is compatible with both EPDM as well as silicone rubber, which are elastomers that are commonly used to connect inverters and batteries. So when we select a lubricant here, we are essentially picking a lubricant that can lubricate an O-ring without inducing any sort of damage. When we look at the L.E.T.S conditions in this case, the load that's being applied to the two interfaces is relatively low, but the environment here is unique because we're dealing with electrical connections that supply over 500 volts of power and 500 amps of current. And the maximum operating temperature in this environment is 120 degrees C, so it's not of a significantly high temperature. And the speed of the application here is static. We're essentially dealing with a stationary application. So in this application, it's probably important to consider a dielectric lubricant because of the specific environment. So for this application, I would choose HP 300 grease because it's a dielectric grease that would suit the specific L.E.T.S criteria here. Additionally, when considering the EPDM elastomer compatibility, we can test HP 300 grease by coating EPDM samples in the grease and then aging the samples for 250 hours at 85°C as well as room temperature to essentially heat age the samples. And then we could take measurements for hardness and tensile strength and then repeat this again for the silicone elastomer O-rings as well. So based on the results we see here on the right, we could see that HP 300 grease can protect electrical connection O-rings in these such demanding environments with minimal hardening or changes in the mechanical properties. The data also shows how HP 300 grease compares to a traditional lubricant that's used as a control. The HP 300, as we could see on the right, didn't negatively impact the mechanical properties of the rubber O-rings, and it also shows great compatibility overall. So overall, we could say that HP 300 is a good fit for this specific application. So for our next case study, we'll also see the use of HP 300, but in a slightly different application as well as a different marketplace as well. In this specific case, we're looking to lubricate the dynamic and static contacts of a bypass switch which is used in a substation environment. And the challenge here is to lubricate the components while an electric load is being supplied directly from the source. Additionally, by lubricating the contacts, we may see a high contact resistance over a period of time. So when choosing a lubricant here, we should be choosing a lubricant that avoids oxidation below a temperature of 55 degrees C, and also keep contact resistance below 60 microohms. So if we apply L.E.T.S to this application, we find that the load requirements here are pretty low. The contact points aren't being held under any significant load here, and the environment here itself is kind of unique because we're again dealing with an energized surface. The component is 1700 volts and 520 amps, and the friction pair here is a silver-plated aluminum alloy and a silver-plated aluminum alloy friction pair. So two of the same material pairs, essentially a metal-on-metal friction pair. And the temperature requirements here are a bit stringent, requiring relatively low temperature at -40 C, and the higher operating temperature range being 55 degrees C. And then lastly, when we consider the speed in this application, we can note that this is also a stationary application as well. This isn't a moving part that we're looking at. So given the more unique environment and L.E.T.S conditions here, we would probably want to lean towards a more intense chemistry, and more specifically because of the lower temperature requirements as well as the requirements for contact resistance. Because of those two given criteria, we'd probably want to lean towards a more fluorinated chemistry. As such, we would probably want to select a grease with a linear PFPE base oil, and one such grease within the portfolio that meets those requirements would be HP300 again. So this grease is a linear PFPE base oil that is PTFE thickened and has PTFE solid lubricants. And because this is a fully fluorinated grease, it would perform pretty well under very extreme, more specialized conditions. I would also specifically choose this grease here because of its ability to provide electrical conductivity over time and also avoid deterioration due to oxidation while retaining functionality in a high voltage environment. So overall, we could use HP300 in two different case studies that are two pretty different environments overall. So we could see that HP300 here kind of works for two different application sets. So now just kind of looking over more general material selection, we tend to look at materials in terms of a good, better, best method. So a standard product for electrical connectors would be MOLYKOTE 111. It's a product that provides protection against moisture and prevent against corrosion. However, if you have an application that requires specific dielectric properties, a more tailored product to look at would be MOLYKOTE G5008, which is a grease that provides excellent dielectric properties, specifically at higher temperatures. And then when you're looking to exceed temperatures above 200 degrees C, you would probably want to look for a almost more intense fluorinated chemistry, which in this case, we could look at HP300, which is a PFPE grease that can offer wide compatibility over a pretty wide temperature range. And then as we look for applications that require plastic and elastomer compatibility, another product that you could probably look at is MOLYKOTE L.E.T. semi-dry lubricant, which is specifically formulated for the lubrication of plastics and elastomers. So next we'll look at selection guidance for plastic lubrication more specifically. So a good standard product to consider for plastic lubrication is MOLYKOTE PG65 Plastislip grease, which is a premium high performance grease that provides protection and a low starting coefficient of friction and good lubricity and high speed compatibility. But as we have additional requirements such as low bleed rates, dielectric properties, or the need for extended lifetime, we could take a look at more tailored solutions. So a good low bleed grease for plastic lubrication that we can consider is MOLYKOTE G1057, which is a low bleed PAO based grease, which provides good long-lasting lubrication with good shear stability. So it's a great product when you're looking at applications that require low bleed. That would be pretty specific to applications in maybe consumer electronics, where you are looking for low bleed, and as well as easy dispensability as well. So a good tailored product for those such applications would be G1057. If you're looking for plastic lubrication with dielectric properties, again, you could look at G5008, which is specifically a dielectric grease. It's a silicone-based grease with a PTFE thickener system, and it's ultimately that chemistry which lends it its exceptional dielectric properties, specifically in high temperatures. If we're looking for a lubricant that requires extended lifetime in regards to plastic lubrication, a good product to consider would be PG75, which is a grease that offers slightly greater bleed than, say, a G1057, which is ultimately why it performs for extended lifetime, because of the oil bleed that offers continuous lubrication. That would allow PG75 to be a good fit for applications involving or requiring extended lifetime, as opposed to a G1057 or a PG65. So next we could take a look at MOLYKOTE capabilities in the lab. So we have a myriad of laboratory capabilities that we offer, and this is specifically so that we can model specific applications in our lab to provide more tailored solutions to our customers. So advanced capabilities that we have within our MOLYKOTE labs include cyclical corrosion, electrical characterization, noise, vibration, and harshness testing, as well as polymer and elastomer capabilities. So essentially what these capabilities allow us to do is to test and model specific products for more specific applications to provide tailored solutions. For example, if we're looking to find a grease for an oil and gas application specifically, cyclical corrosion becomes a test method that becomes more critical for those applications in order to find tailored solutions to applications requiring resistance against water washout, or corrosion mitigation, crevice corrosion mitigation, or whatever application issues you would see in those specific markets. Electrical characterization testing also allows us to find tailored dielectric grease solutions for specific electrical applications. And polymer and elastomer capabilities, compatibility testing allows us to find tailored solutions for the lubrication of seals and O-rings for a variety of different markets as well. So overall, we have multiple products within our portfolio that are designed to offer a breadth of chemistries and product offerings for multiple application sets, as well as provide more tailored solutions for our customers given their specific application needs. Thank you.